So hello everyone, in this lecture I am going to discuss about the radars, including in which I will include the Doppler radar and the contrast CW radar with its advantage and disadvantage. So first of all, starting with this radar range equation. So the radar range equation relates the range of the radar to the characteristics of this transmitter receiver antenna, and antenna it is used as a tool to help this in specifying radar subsystems. So if the transmitter delivers the PT power and into the isotropic antenna, then the power density will be defined, which is defined as for distance r is PT upon 4 pi r square. This is the incident power is so we can find the power density from the directional antenna multiplying with this gain. So the power density is PT by 4 pi square. I will multiply with this G, and I will get here the power density from the directional antenna. So the power density from the echo signal at the radar is equal to the difference of this PT G by 4 pi square minus into rho upon 4 pi r square. So the power delivered to the load is nothing but the multiplied by the delivered to the receiver or load is the total power, this signal multiplied by this aperture area, that is AE. Now the maximum range of R maximum is the distance beyond which the target cannot be detected due to the insufficient received power. So what will be the maximum range of this what will be the maximum range for this maximum range of the distance? It will be equal to R maximum. It will be equal to this PTG upon 4 pi r square, 4 pi upon 4 pi square into S minimum, ki power 1 by 4. So how will you get this? So for calculating this minimum power which the receiver can detect is called the minimum detectable signal, and we can get the value of this R maximum by dividing this total power delivered to the receiver with the minimum detectable signal. The gain of the antenna is directly related to this effective area and is given by G is equal to 4 pi AE upon lambda square. If the radar transmits and receives the signals are the same, then R maximum will be equal to this PT upon PT G square lambda square sigma upon 4 pi cube into S minimum, and R maximum will be this. Now what is the radar frequencies? So this is the table from where you can see that the range of frequency, wavelength as well as applications. Now coming to the PRFs and range ambiguities. So PRF is the number of pulses transmitted per second. It is determined by the maximum range at which targets are expected. So PRF is equal to the reciprocal of the pulse repetition period, and its unit is hertz. So PRF basically in simple radar system, echoes from the targets must be detected and processed before the next transmitter pulse which is generated if the ambiguity is avoided. So how will I find the range beyond the targets appear? Range beyond the target. So the range beyond the target, that is maximum and ambiguous range, is equal to C by twice of Fp, where C is the velocity of propagation and Fp is the pulse repetition frequency. So echoes received from the interval exceeding the pulse repetition period are called the multiple time around echoes. These can result the erroneous range measurements. The echoes from an ambiguous target will appear at the same place on the echo and each sweep. However, echoes from multiple time around targets will spread out. The methods to mark successive pulses to identify multiple time around targets, including changing amplitude, pulse width, frequency range, phase or polarization from pulse to pulse. Now coming to the Doppler radars. The radars radiates electromagnetic waves towards the targets for detection and also to obtain details of the target. When the target is stationary, the frequency of the received echoes is constant. However, when the target is moving, the frequency of the received echoes is found to be different from transmitted frequency. If the target approaches the radar, the frequency is increased, and if the target moves away from the radar, the frequency is decreased. So that is in the moving target, there exists a frequency shift in the received echoes. The presence of frequency shift is the received echo signal in the radar due to moving target, that is known as Doppler effect. The frequency shift is known as Doppler frequency. Now, how will you determine the velocity, Doppler velocity? If the target is in motion, the distance r and phi are continuously changing. So, a change in phi with respect to the time is equal to a frequency, that is Doppler angular frequency. Doppler angular frequency omega d is nothing but 2 pi fd. 2 pi fd is nothing but change in phase d phi by dt with respect to time. So phi is nothing but 4 pi r by lambda, and I will get here 4 pi by lambda into dr by dt. Dr by dt is nothing but the velocity. So I will get here 4 pi by lambda into v. So v is nothing but the Vr. Fd is equal to 2Vr by lambda. So Fd is Doppler frequency shift in hertz. Vr is relative velocity of the target with respect to the radar, and lambda is the wavelength in meters. So the relative velocity is given as Vr is equal to V cos theta, where F and Fd is equal to 2V cos theta by lambda. When theta is equal to 0 degree, the Doppler frequency is maximum, because cos 0 will be 1. In that case, Fd will be equal to 2V by lambda. And in case of theta is equal to 90 degree, the Doppler frequency will be 0. And this will be the condition, and the trajectory is perpendicular. In that case, the trajectory is perpendicular to the radar line of the signal. Now, coming to the next type of radar, that is continuous wave radar. A continuous wave radar system emits electromagnetic radiation at all times. That is, it transmits continuous electromagnetic waves and receives reflected echo signals from the objectives. So, conventional continuous wave radar cannot measure range as the energy is transmitted continuously. It can measure the instantaneous rate of change in the target range. That is accomplished by a direct measurement of the Doppler shifts of the return radar, of the return signal. The Doppler shift is a change in the frequency of the electromagnetic wave caused by motion of the transmitter, target, or both. A simple continuous wave radar consists of a transmitter, mixer, beat frequency amplifier, and indicator. So it has shown in this block diagram. It consists of transmitter, mixer, beat frequency amplifier, and indicator. So transmitter basically continuously emits the electromagnetic signals towards the target. And mixer is used for heterodyning the transmitted signal frequency and reflected echo signal frequency, which results in Doppler frequency. And beat frequency amplifier eliminates echoes from stationary targets and amplifies the Doppler echo signal to a level where it can operate an indicating device. And indicator is used to pair earphones or frequency meters. If the target is in motion with a relative velocity Vr to the radar, then the received signal will be shifted by an amount plus minus Fd. And the plus sign is associated with the Doppler frequency. If the distance between target and radar is decreasing, that is closing to the target, and when the received signal frequency is greater than the transmitted frequency, and minus signal associated with the Doppler frequency applied if the distance between the target and radar is increasing, when the received signal frequency is less than the transmitted signal frequency. The purpose of this beat frequency amplifier is also to eliminate the echoes from the stationary targets and to amplify the Doppler echo signals to a level where it can be used to operate an indicating device such as the pair of earphones or a frequency meter. Now, what is the advantage of this continuous wave Doppler radar? The CW Doppler radars are not pulse and simple to manufacture. These radars have no minimum and maximum range. and maximize power on a target because they are always broadcasting. These have the ability to measure velocity with extreme accuracy by means of the Doppler shift in the echo frequency. The detected reflected wave is shifted in the frequency by an amount which is a function of the relative velocity between the target and the transmitter receiver. The range data are extracted from the change in Doppler frequency. Now, disadvantage of a continuous wave radar: when a signal antenna is used for both transmission and reception, it is difficult to protect the receiver against the transmitter, because in constant to pulse radar, both are on all the time. These are able to detect only moving targets, as stationary targets will not cause a Doppler shift and the reflected signals will be filtered out. And CW radars cannot measure range, where range is normally measured by the timing the delay between a pulse being sent and received. Now next is the FMCW radar. In order to overcome the inability of the CW radar to measure the range, a signal that constantly changes in frequency around the fixed reference is used to detect stationary objects and to measure the range. The frequency is generally changed in a linear fashion so that there is an up and down or a sawtooth like alteration in frequency. If the frequency is continuously changed with time, the frequency of the echo signal will differ from that transmitted, and the difference delta F will be proportional to the round trip time delta T, and so the range R of the that will give the range of the target. When a reflection is received, the frequency can be examined, and by comparing the received echo with the actual transmitted frequency, the range is calculated. So this is the block diagram of the FMCW radar, including transmitter and receiver side. The transmitter frequency is continuously varied at a known rate, and the reflected signal frequency is compared with the frequency of transmitted signal. And it measures a slant range by determining the difference between the frequency of the reflected signal and the frequency of the transmitted signal at an instant of time when the reflected echo signal is received. It also measures the bearing and elevation angle of a target from the position of the antenna corresponding to maximum reflected signals. So we can measure the height of the target by multiplying the slant range and cosine. The range R is equal to V naught delta T by 2, where delta T is equal to T into delta F upon F2 minus F1. And from here we can calculate the R, where V naught is the velocity of EM wave, T is the period of sweep from F1 and F2. F1 is minimum frequency and F2 is maximum frequency. V naught is free space velocity of EM wave, and delta F is the difference between the transmitted and received signals. Now coming to the pulse Doppler radar. A pulse radar that employs, so this is the block diagram where you can see that here we are using the pulse modulator, power amplifier, CW oscillator, receiver and indicator. So a pulse radar employs the Doppler shift for detecting the moving targets, is either an MTI radar or a pulse Doppler radar. The pulse Doppler radar has high pulse repetition frequency to avoid Doppler ambiguities, but the MTI radar has a pulse repetition frequency low enough not to have any range ambiguities. It has many ambiguities in the Doppler domain. The continuous wave radar can be converted into a pulse radar by providing a power amplifier and a modulator to turn the amplifier on and off. The main difference between this CW and pulse Doppler radar is that the some portion of the continuous wave radar that generates the transmitted pulse is applied to the receiver as the local oscillator reference, which is needed for the Doppler frequency detection. So this is the block diagram of this MTI radar. It consists of the pulse modulator, power amplifier, duplexer, mixer, IF amplifier, coho, and phase detector. This is the MTI radar, and this is all about the radar system. Thank you.